Hello again everybody, welcome, and today we look at projectile motion and introduction. Now, what does using a hose, kicking a football, shooting a cannon, and skimming on water all have in common? Shooting a cannon and using a hose may not be sports, but they all represent projectile motion. But what is a projectile? A projectile is any object that is launched, thrown, hurled, shot. You get the idea, right? Well, the motion attained is called a projectile motion. However, the path of the body formed is called a trajectory. This path is drawn to assist in solving questions on projectile motion. What questions, you may ask? Well, what angle should a footballer strike a ball in aiming for a goal? How far away should you be to shoot hoops in basketball? At what speed should a rugby player or a quarterback move to receive a high ball? While all these examples involve other movements and other factors, projectile motion forms the basis by which these events can be accurate. But before we get to any calculations, let's look at some key characteristics of projectile motion. There are two main forms to begin with in representing a projectile motion. Now, our diagram shows the path of an object fired, which is called the trajectory. Our first example is an object thrown horizontally from a height. This height can be known as S or H, as we will see as we go along. In this example, that height is a cliff. As you can see, the path of the object obtained, or trajectory, is actually not linear. The horizontal surface we take as the ground, and our horizontal initial velocity is known as u. The distance from the foot of a cliff to where the object lands on the ground is known as the horizontal distance. This is also known as the range. Our second type of diagram is actually an object projected from a horizontal surface, for example the ground. In this case, the path or trajectory begins and ends on the horizontal surface. Drawn at a tangent or vector to the initial movement is the initial velocity u. Now this takes place at the same angle formed that is projected, that value being, of course, theta. Once again, the distance between the point of release to the point of where the object lands is called the horizontal distance or range. Now let's look at a few things that we should note about projectile motion. In both cases, air resistance is considered to be negligible. Now, remembering that gravity acts downwards, consider a person jumping on a trampoline. That person accelerates downwards towards the trampoline predominantly because of gravity, thus experiencing a gravitational acceleration. This gravitational acceleration is known as common g. This forms the vertical component of acceleration, but since acceleration is a change in velocity over change in time, then this vertical component of velocity changes as the object moves. Which brings me to my next point. Why are we speaking about components? Well, because projectile motion involves the use of vectors. That is, we can separate each vector quantity to be more specific, into a horizontal and a vertical component. Let's consider our second diagram for projectile motion, where an object is projected from a horizontal surface and returns to that horizontal surface, forming a trajectory as seen in the diagram. Our initial velocity is given as we mentioned, a tangent or vector known as u. But that initial velocity drawn as a tangent to that curve, that initial part of our journey, is still at an angle theta, as we've seen, to the horizontal surface. Using vectors and of course trigonometry, we can now find our two components of that initial velocity. The two components being the horizontal component, which lies along the horizontal surface or horizontal plane, and the vertical component, which lies vertically. Using our vector given, u, we can now form a triangle of vectors. Notice that the initial velocity u is actually a resultant vector, which means it follows a different direction or sense from the other two vectors involved. For more information on how to draw a vector diagram, please see our two videos on resolution of vectors and vector resolution. As with previous vector resolution, we use trigonometry, our sine and cos ratios, to find the horizontal and the vertical component of initial velocity. We're using sine of the angle theta, we get our vertical component of velocity given as uv equals u sine theta. Now, because of that, we can now see that our cos of that very angle theta will give us the horizontal component of velocity, that being UH equals U cos theta. Now, just a simple reminder, our initial velocity is given a symbol of lowercase or common u, whereas our final velocity is given as common or lowercase v. Now, using this trajectory, we could separate our initial and final velocities as being the left side and the right side of the diagram respectively. I'll explain in a little bit. Let's consider points at which that object along this trajectory moves. They are represented by the dots seen on the diagram. At any of these positions, that object experiences both horizontal and vertical components of velocities, not horizontal or vertical only. Now, what does that mean? Horizontally, because gravity acts vertically, our horizontal components of velocity are all the same. So whether they are called UH, meaning initial horizontal components of velocity, or VH, final, which is on the right hand side of our diagram, final horizontal components of velocity, they are all the same. This is because what projectile motion considers is the pull of gravity being that sole force acting on the object. As mentioned before, air resistance is considered to be negligible. On the left side of the diagram, the initial vertical components of velocities all act upwards, shown in pink, whereas on the right hand side, the vertical components of velocity are all acting downwards. These can be represented as UV and VV respectively, where UV represents the initial vertical components of velocity on the left of our diagram, in pink, traveling all upwards, whereas VV represents the vertical final velocities of the object or this object being projected, all acting downwards. Again, to reiterate why the vertical components change is because gravity acts vertically, not horizontally. So, whether the vertical components are called UV or VV, meaning initial or final vertical components of velocity, they change. However, the horizontal component of velocity is not affected by gravity, so it remains unchanged. But what does this mean? If the horizontal component of velocity remains unchanged, meaning that we can call it UH or VH, it's constant, what does that mean about when it comes to at least the horizontal component of acceleration? Well, since acceleration, by definition, is change in velocity over change in time, and of course, the horizontal component, therefore, of acceleration is a change in horizontal velocity, or the horizontal component of velocity over time. If that horizontal component never changes, then we can expect that the change in velocity horizontally is zero, thereby making our horizontal component of acceleration also zero. However, this is not the case with the vertical component of acceleration. Since the vertical components of velocity are affected by the pull of gravity, then the vertical component of acceleration, well, that is actually gravitational acceleration, given as approximately 10 or 9.81 meters per second squared. Because these are vector quantities, those values can either be positive or negative. But an important point to note, as reiterated before, the vertical component of acceleration is g. So if, for example, we choose the upward direction as being positive and the downward direction as being negative, then depending on the direction of the velocity of the object, it tells us what direction this object accelerates as well, if those values are in fact positive or negative, as we will see in our diagram and our example. Also, since we ignore air resistance, then we make an assumption. At our maximum height, assuming of course this object forms a uniform trajectory, at our maximum height, we assume that the time it takes for that object to reach from its starting point to a maximum height is actually the time it takes for that object to move from that maximum height to its final endpoint, which is of course the same horizontal position. So in our diagram, if t1 equals t2, then our time of flight, which means the time at which the object remains in the air, is actually 2 times, or 2 multiplied by our t values. For example, 2 times t1. And our final point, projectile motion uses the equations of motion. So in addition to using vectors, we also apply the equations of motion. V is equal to u plus at, s is equal to ut plus a half at squared, and of course v squared equals u squared plus 2as. Now let's consider s equals ut plus a half at squared. Can we use that equation to find our total horizontal distance, also known as mentioned before, our range? It is important to note that s in our equation of motion, or kinematics equation of motion that is actually our vertical distance, or displacement, more specifically. Whereas in pink, our horizontal distance is called our range. We can call it xh or r, any of those two values. But can we use this equation to find our value for range? Let's see. Let's call our horizontal distance xh. Then our equation of motion becomes xh equals u h by time plus a half by, of course, the horizontal component of acceleration ah multiplied by time squared. Now we use all our vector quantities as our horizontal components: displacement, velocity, and acceleration. But an important point to remember, don't forget, AH, or horizontal component of acceleration, was actually 0. So, what does our equation now become? Our horizontal displacement or horizontal distance is actually called our horizontal component of velocity, which of course we mentioned was u cos theta at the very beginning by time. This is our equation for range, or that horizontal distance from the start to the finish of the movement of this object or trajectory. Hope this video was helpful. Our next projectile motion video will be one where we will work out questions involving a projectile motion. Feel free to check out the other videos on this channel. And before you go, what game involves projectile motion? Well, Angry Birds. Be that cool, guys.